Hello and welcome to another LeetCode video. Today we're going to be working on unique paths 2. And so in this problem, you're given an n by n integer array grid, and there's a robot on the top left, and you are trying to get to the bottom right corner. And we need to write how many different paths the robot can take to get there. So in this first example, simply you can just check, like, there's only two paths, right? So there's this path here, and there's this path here. So there are two paths here total, which is pretty straightforward, right? We either go right and then all the way down, and then we go left and all the way down. And then in the second example, there is only one path. We have to go this way. Okay, so we're going to get rid of this second example, and we're going to focus on the first example pretty much. So let's get rid of this, actually, and let's just focus on this example. And let's focus on, like, what are we going to be doing and what are the choices we have at every step. And while this is simple, this is still going to be a good one to do. Okay. So essentially, if you think about it, at every single place, we have two choices. We can either go right or we can go down, right? And so those are the choices we have. And so the number of total unique paths is going to be the number of paths that you can go right. Right, so the number right, let's actually make it a little bit cleaner here. So let's do this, let's delete this. Okay, so let's actually do this. So we're gonna write number right plus number down, right? And so essentially this is a DP state where, let's say this was 0, 0. So if this is like 0, 1, 2, and this is 0, 1, 2, the number of paths for here is going to be, if this was our whatever function it is, let's just say we have a function where we have dp and then we have a row and a column. Let's call that like rc or something. It's actually going to be a function, not an array. So there we go. So we have this, and we can go down or we can go right. So the number of paths from 0, 0 is going to be the number of paths from 1, 0 plus the number of paths from 0, 1, right? So this 1, 0 means we went down. So we can just take the number of paths from here and the number of paths from here, add those together, and that'll be the number of paths from here. That's like our recursive state, essentially, for this problem, right? Anytime you have two choices, and those are the only things, so you can either move, and it tells you, right, you can't move up. You have to go down or right. And so you can either go here or here, and we just add those up. And then let's think of, like, what issues we can run into and what's a base case for this problem, essentially. So let's write some of these things down. So we're going to have a dp function. Let's think of some base cases. So what are some base cases? So first of all, if we hit the star, that's a base case, right? We hit the star. What should we return? Like, let's say we're at the star. What should we actually return in that case? Well, we want to add up all the total paths. So if we hit the star, we can just return 1, as in like successful path, right? That's one case. What about we hit an obstacle? Like, we start at an obstacle. Like, let's say we are calculating these paths, and like this is this plus this, but now we're here, and this is this plus this, but now this is an obstacle. So like, how much should this be worth? Well, any path that starts at an obstacle should be worth 0, right? Because it's an invalid path. And they tell you, a robot path cannot include any square, so anything that starts at the obstacle or includes the obstacle will just be 0. So for example, if we're here, like let's say we're over here, when we take the right and the down, we're not going to include the down where we are, but this down should return us to 0, right? So that should be 0, so we're just going to write a 0 over here, and the star is going to be worth 1. So if we hit an obstacle, we are going to return, let's just actually, that's fine, I guess. A little bit higher. So we're going to return 0 because that's an invalid path. Okay, now what other stuff do we need to take care of, right? So we hit the star, we return 1. We hit an obstacle, we hit 0. We can go right or we can go down. Okay, we got that. It's kind of like the coin change problem, but what other things do we have to take care of? Like, is there any other base case? Yes, obviously, right? So we are out of bounds. So if we're out of bounds, we're also going to return 0. So like, let's say we're over here and we try to check the right value and the down value, and this right value is out of bounds. Well, You could check that before recursing, but in our case, I'm just going to check for all of that. I'm going to check for out of bounds and obstacle all in the start of the function. And then if it's any one of those, we're going to return 0. Now there is also a caching mechanism, because let's say there wasn't an obstacle, you can get to the same place multiple ways. Like let's say this was not an obstacle, well you can actually go to this place this way, right? You can go right and then down, or you could also go down and then right. So you're getting to the same place, and the number of paths from this location doesn't matter how you got there. So we are also going to have a cache. So that's another base case is cache. Just return that value. Okay, so that's good. So now we kind of have, so we're going to, at every case, this is our recursive case. So let's write that down as well. So recursive case is going to be add the answers from dp of down plus dp of right. And this is what these are, right? So this is dp of going down and the dp of going right, and that's a recursive case. So the number of paths from here are the number of paths from here plus the number of paths from here, because we can go to either one from that. And so that's the recursive case. And we have a base case, we have a cache, we have a recursive case. So we kind of have everything we need for this, like, and this is like a pretty straightforward problem if you know DP, right? Like this is one of the simpler ones. But yeah, essentially we can only go right and go down. So this is our recursive case, and then we have a base case, and then we're out of bounds. We hit an obstacle, we hit the star. There are a couple things you have to check for, but we're actually going to be doing all that as we are doing our recursion. So you do have to be careful. So like the cases you have to look for, depending on where you're checking for the obstacle. Let's say the obstacle is actually over here. If the obstacle is over here and you don't check for that, like let's say you check for an obstacle before recursing, then this is gonna give you the wrong answer. So that is like an edge case that you have to look out for. The obstacle can be here, and then the obstacle can actually also be here. You have to check for both of those. That's why you have to check for the obstacle either right as you enter the function, or you just have to check for those outside of the function or whatever you want to do, but those are edge cases you have to look for. Okay, so now that we know all that, now we can actually look at the memoization solution. And so here it is. I'm actually gonna uncomment this. So we have a visited hash set, as always, or hash map. We have a rows and the columns. That's going to tell you how long it is. And then, so this is called DFS, but you can call it DP. I think it's probably more accurately DP, but either one works, you know, whatever. And so this check is to make sure that your row and your columns aren't out of bounds, right? You don't want to go too far right or too far down. That should give you 0. And also, if we hit an obstacle, that should also return 0, like I said before. And this is the check that we hit the star. So if we hit the star, we want to return 1. Finally, we have the cache. And then, like I said, we go right and then we go down. So row plus 1 is going down, column plus 1 is going right. And so we can test this. And so it did get accepted. And you can see it's like pretty efficient time, but memory, it's not super great. So let's just try to figure out like how do we make this a little bit better. And for trying to make it better, what we're actually going to do is we are going to take this and we're going to draw it down here. And we're going to come up with a bottom-up solution, and then we're going to come up to see if we can have any optimizations. So we're actually going to draw this over here, and it's going to be 3 by 3. So I think I can actually hit the, there we go. Yeah, I got to learn how to use this eventually. So I can actually hit this. Okay. So now what we need to do is, I think this should be that. Okay. Okay. So now we're going to label these. So 0, 1, 2, 0, 1, 2. And then we are going to also put a star over here. And we are going to, actually, let's not put a star over here. Let's just more figure out like what that value should be. And then the person's going to be over here, and there's an obstacle here, but we're not going to draw that in. We're just going to say that that exists. Okay, so we're going to make a DP. Now, there is one way you could make this space optimized, but I think it's a little bit cheating, where you are just changing this this matrix that's being passed in place. You could do that, but some interviewers might say, like, let's not do that. So you could totally do that in place. That would totally work if you wanted to. But we're going to show the bottom-up solution, assuming you can't just change it. So we're going to create a matrix that's the same dimensions as our other matrix. Now we want to initialize, we want to check first, is this or this point an obstacle? And then if either one of these is an obstacle, then we can't have an answer, right? Because we start here. So if this is an obstacle, we can't go anywhere. And then if this is an obstacle, then you're covering up your star. So we're just going to check for these preemptively. Now, once we check that those are fine, what we're going to do is we're going to put a 1 here, and the rest of these are going to be zeros. I'm not going to draw them in, but essentially the rest of these are just going to be initialized as zeros, and this is like our base case where we have a success. Okay, so now we need to fill out the rest of this, and then we need to return this section, right? And so this part is pretty straightforward. The way we're going to fill it out is we're actually going to go row by row, and then we're going to go up, or sorry. So if you look at our recursive case, we have to add the answer of going down and going right? So like if we're over here, all we have to do is just what's down here and what's to the right. And so let's fill out this bottom row. So if down is out of bounds or if right is out of bounds, we're just going to say that's 0. You could also put in filler rows like I did in the coin change, where you could just put in a filler row here of zeros if you wanted to. If you never wanted to be out of bounds, like this is totally fine. Or you can just have if statements making sure you're not out of bounds. Like that would be fine, or either one would be fine. Okay. So we're gonna say, okay, let's take the right value and let's take this value. So this value is 1, this value is 0, so that's gonna be 1. Now we're gonna do the same thing here. Let's take this value and let's take this value. So technically also what you could do as like a shortcut if you wanted to is you could initialize your bottom row to be all 1s. Because if you think about it, you can never go down, and this is always 1. So you could do that as a shortcut. You could initialize this to be all 1s. It will always be 1s initially. Could totally do that, totally fine. Okay, so now we need to fill out these rows. So this number, right is out of bounds, and down is a 1. So this is going to be a 1. Now here, right is 1, and down is 1. So that's 2. Right? So essentially doing this recursive case where we're saying let's take the down and the right, and let's add those together. So here we have a 1 and a 2, so we're going to have a 3. Now here, right is out of bounds, and down is 1, so this is going to be 1. So that's the other thing you could do if you wanted to. You could fill this column and this column to be 1. Because essentially here, you only have one option. If you're on the bottom row, you can only go right, and if you are on the last column, you can only go down. Okay, so now here, we have this plus this, which is 3. And now we have this plus this, which is 6. Okay, so let's see if we did that correctly. I think I'm actually going to have to look at the problem really quick. So this is a little bit, there was a mistake. Oh, yeah. So the mistake we made, we did make a mistake. So the mistake we made, let's go back. So this part is all correct. But the mistake we made is there's an obstacle here. So that's the thing you can't just like blindly add these, because that will always give you the same answer, honestly, too, right? We have to check for obstacles. So what we forgot is at every single place, we're actually checking for an obstacle. And then if there is an obstacle, we're going to make that value 0. So there's only an obstacle in the middle. So when we look for this value here, this value is going to be 0 because there's an obstacle here. So any path starting from here is going to be 0. So that's the thing we missed. So there's only one obstacle here, but like if there was an obstacle here, this would be 0 and so on. So these are all 1s just because you can only go right here and you can only go down here. But now let's do the rest of them. So let's look at this one. There is no obstacle, so that's what we forgot. So we have to check there's a 0 and then there's a 1. Okay, so that's going to be 1. Now here, there's a 1 and there's a 0, so that's going to be 1. And now finally in the last place, there's a 1 and there's a 1, so that's going to be 2. So essentially we're working backwards, so let's write that down. So dp of ij, let's call it, equals 0 if there is an obstacle. Otherwise, add dp of I plus 1 j plus dp of I j plus 1, assuming they are in bounds, right? So if they're not in bounds, then we're just going to add 0, right? So we have to check for the obstacle. And then if the obstacle is there, then we make it 0. Otherwise, we add the right and the down. So that's how we do that. And let's actually take a look at the solution here. So this is like one of the easier dynamic programming problems. So I would suggest to code the memoization and the bottom up, because this is like as easy as it gets for a 2-dimensional DP. So here's our bottom up. So let's try to run that. And let's comment this out. So we need to actually comment that. So let's try to run that. And you can see it is more efficient, but this is a little bit random. This should technically be the same as the memoization solution because we still do have a 2D array. So now we have one last optimization to make. And this last optimization is, notice that just like in the coin change, for every single index, we are actually only looking down one row and right one, like we're only looking down one row and right one column. So if we're on this row, we're never checking down here. And so anytime you have that where you only need the previous row to fill out your row, then you don't need this whole matrix. You just need 1 or 2 rows. So we're going to redo this. We're going to redo this whole thing. So we are going to like leave it the way it is here. So this is going to be, let's just fill that out here. So this is 1, 1, 2. We are going to leave that, but we're actually going to redo this doing only 1 row. So we're going to make 1 row. It's going to be a length, whatever this is, same length. And we can actually make it ones. I don't think I made it ones in my code, but you can. Because, right? Because the only option you have is to go. So actually, no. You can't. Sorry, you can't make it all ones, and you can't make this all ones because there might be an obstacle, right? So there might be like an obstacle here or here or here. So you can't actually make it all ones. So instead, what we have to do is we are still going to check for the star or for an obstacle here or here. So if there is an obstacle on the top left at our start position or at the star, we can't have any solutions. So we would return 0. But now what we would do is we would just say, okay, this is our bottom row. Let's make this 1 because this is like our goal. This is actually where the star is. Now let's fill out the rest. Okay. And so that's what we're going to do. So this is essentially going to be initialized to this. Now we are going to fill out the rest. And this represents, so let's actually write a row in our column here just to let us know like where we actually are here. So our columns will always stay the same, but our row will change as we move up. So we start at row 2. And we say, okay, for this value, is it, let's actually change the color as well. Can I think? Yeah. Okay, perfect. So I can move through these quickly. Okay, so what we do is for this, we need to check, is it an obstacle? And this corresponds to this right here. So it is not an obstacle. Perfect. Okay, well, if it's not an obstacle, then let's go down and let's go right. Well, there's nothing down, so we'll make that 0. But there is something right. So right, there is actually a 1. So we're just going to make this a 1 now. So let's do that. Okay, what about this? Is it an obstacle? No, it's not because it corresponds to this value. So is there something down? No, there's not. And there is something to the right. So we're going to add the down and the right, but there's nothing down. So we're going to delete this, make this a 1. And now we're done with the row. And you can see that like this row and this row are exactly the same, which is the idea. So now that we have that row, like obviously when we tried to go down, we couldn't do anything. But if you think about it, we never actually have to go down anymore. Because if you think about it, look what happens here. So let's say we change this color to this, and then we delete this. And now this is supposed to represent the row 1. This is supposed to represent this row. Okay? So what we're actually going to do, we're going to need to make a few changes, but it's totally doable. So these numbers represent this row here, right? This is like the down part. So if we're calculating this row, we need to get the down and then we need to get the right. So we already have the down. The down is already here. So essentially, if we're doing it in place, we don't need the down anymore. We just need the right. So all we need to do is we can write this in actually. So we don't need to check the row below because we already have those values since we are doing in place now. Or we're not really in place, but we're only doing 1 row. So because we're on this row, we already have these values, right? In our initial thing, these were all zeros, so we did need to take the down values, but now they're not. And so now we actually have all these values. So now we need to do the same thing. We need to check if it's an obstacle, and if it is, then we need to make it 0, and if it isn't, we need to take the value to the right and add it to it. So we're going to check over here. Is that an obstacle? No, it is not. That's this value here. But there is no value to the right. Okay, what about this middle value? So this middle value is actually the obstacle, right? This is 1, 1, which is this value here. So because this is an obstacle, we need to make this 0 because there can't be any paths coming from it. Now for this last one, that's over here. So it's not 0. So we need to, remember, we don't need to check to the right, or we don't need to check down anymore. We need to check to the right. So this is this value here, right? So because it's 0, we already have the down value. So we need to add 0, which would just be 1. Okay, so now we have this row done, and you can see that row is also equal to this row. It started off at 1, 1, 1, but because this was an obstacle, we changed that to 0. Okay, now let's change that row to the last row that we have. And so we're essentially doing the same kind of nested for loop, except now we're just storing everything in one row because we realize we don't need this whole matrix. We're just only relying on the row before. So now we're on this row, and we have all these numbers down here. So this is that down section. That's already done. Now we need to check, is it an obstacle? No, it's not. So that this index corresponds over here. That's not an obstacle. Okay. We can't, there's nothing to the right. Okay, what about this index here? This index corresponds up here. That's not an obstacle. There is something to the right, so we need to add that in, right? So we're going to add that in, and we're going to say that's 1 now. Okay. Now, what about this one? Is this an obstacle? This corresponds to the starting index now. No, it's not. And there is something to the right, so we need to update this to add that right value. And now we have this thing, and that's this thing. And now we just return this value here, right? So we don't want to make these all ones. We want to start with an array that's length of this bottom row, and that right value needs to be a 1. So it's all zeros and then that. And then essentially we're doing the same thing. The time is the same, but now we're doing that in place. So this is the space optimized bottom up, and we're also not cheating. I think in the editorial they just did this in place. You could totally do that. You could just do a bottom up with this matrix in place. That would technically be O of 1 space. But also you might have an interview that says, like, don't mess with your data, you need to do something else. So you could do it in place if, you know, and then that would be totally doable because essentially it would be a little bit modifications in your code, but it would be totally fine. Like you would just check, do I have an obstacle or not, and then modify it in place. It would look pretty similar to this code, but it's also kind of cheating, and this is the harder solution that you can't do in place. So I just wanted to show you that one. So let's look at the code for that. So this is the bottom up, and then we have the space optimized bottom up here. So I should comment out this one. And now we can actually, I just wanted to hide the rest of it for now, but now we can actually bring all this up. So let's actually bring this up here. And let's get rid of that, and then we can test that as well. And so this needs to be commented out. But essentially you can see like this code and this code, so I'll comment it out in a second, is pretty similar. Like it's almost the same. Like we have rows and columns, we check for this out of bounds, and now instead of making a 2D array, we make a 1D array, we make the last index 1, and then this loop is basically the same. There's like one small difference. So the space optimized bottom up isn't like that much harder once you understand the bottom up, but also usually space optimized doesn't work for harder problems because usually harder problems don't just, like if this was a hard dynamic programming problem, usually don't just involve the value right below it and to the right. It's more like you can check a bunch of different locations. But yeah, so let's try to test that. And so that does work. And you can see like this one's more efficient. It's kind of, it depends on the LeetCode test exactly. Like I don't know what parameters they have. They might just be really small. Yeah, so these parameters are really small. So these are only 100. So this is like 100 by 100. So you're actually not saving this much. But if you were to test like a huge matrix, then that would make a difference for you. Yeah, so let's go through the time and space for all of these. So essentially the time for all of these is going to be m by n, because you do have to, at the end of the day, look through your entire matrix, right? You do have to check every single path. So there are m by n states. And so that part is going to be m by n for all of these. But the space for the recursive and the bottom up is going to be m by n, because for your states that you're saving in your visited or in your 2D array, you're saving this entire thing. So that's m by n. So either here or here, this is m by n. But for the space optimized, it's only the length of a row. So it's the number of columns. So what's the number of columns? It's n, I think. Yeah. So this is O of n in space for the space optimized. But yeah, I would strongly say like this is one of the easiest DP problems. So if you're learning DP, I would try to do this. I would try to go through like, okay, let's do this top one, let's do the second one, let's do this third one. Make sure I get everything because it only gets harder from here. So if you have like holes in your knowledge for these problems, like it's only going to get harder. So don't think like, oh, I'll just like let this one go and then whatever. Like this is one of as easy as it gets for a 2D DP problem. And so I would definitely make sure to do that. And I will be including the code. And so if you want to convert it to like whatever, you know, let's say like you do Java instead of Python, you can just chat GPT to convert this to whatever language you want. So that's kind of convenient. But yeah, that's going to be it for this problem. Hopefully you liked it. And if you did, please like the video and sub to the channel. It really helps grow it. And I'll see you in the next one. Thanks for watching.